Okay, we're back again. Just make sure the date is right. Yep. Advent of Code 2022 Day 8. Didn't do so well on yesterday's problem. And looking through some of the solutions, I feel a bit foolish because my initial inclination was to solve it kind of the efficient way, but for some reason I thought part 2 would be trickier and kind of require us to actually keep track of the files for some reason. But I guess interesting thing to note about the problem, the way I ended up solving it with parsing this and creating the graph structure and then doing a DFS on that to compute the size of each directory. But actually, implicitly, this is just a I forget what it's called. That type of DFS traversal where it's like in order, or like something traversal of DFS. And so if you just read this line by line and push into a directory if you see a CD, pop out if you see a CD dot dot, and then whenever you see a file, you kind of add that to the cumulative sum of each directory that you've pushed into, that'll actually give you the answer. And you don't have to construct a graph, and you don't have to do the DFS, because implicitly this is giving you the output of a DFS. Yeah, it's like an in-order traversal, something like that. I forget my algorithms specifically. But yeah, so that's how a lot of people ended up solving that this problem, and I think it's particularly clever. So just wanted to call that out. Also, the bug with my code that I couldn't figure out yesterday was I was assuming every directory name was unique, but you can actually have, you know, 2 folders named foo in different parts of the file system. And the way that I was kind of caching different sizes of directories was by name, and you would overwrite the same name if you had a collision. And so that's why I was undercounting directories for part 1, because I was accidentally kind of overwriting the sizes and not accommodating for the fact that 2 directories can be named the same thing in different parts of the tree with different sizes. But we're gonna try to brush that off, make sure the stream is doing things, and just focus on day 8. If the pattern of problems is right, we'll be a little bit easier today, but we'll see what happens. You never know. All we can do is read better and code less buggy, and hopefully get a more exciting song. Okay, stream should be off delay now. Stream should be going live because, yep, okay, and I should see it there. Excellent. If nothing else, I'm getting the hang of all of this OBS shenanigans, so that's nice. Why did this open twice? Oh yeah, also we're kind of seeing a bit of the picture come together. It looks like it's a river with like a delta, some luscious forests or something around here. I'm excited to see how this turns into a holiday scene. Left to 5. cur is greater than n. Wait, if cur is greater than n, yeah, you want to break else equals 1 and n minus equals or n equals n, right? I think this is right. Then we have to do the same thing for all the x's. We start at the bottom. This should be minus. Y here. This is x minus y. We want to decrement y. Then print total. Hello. Let's see. Visible from outside the grid. So visible if all of the other trees between it and the edge of the grid are shorter than it. Is that not the correct logic? The top right one. Trees visible on the edge of TC4. That makes sense. Am I counting? Maybe I'm over counting. Oh, probably over counting here. That's 14. Oh, okay. Well, we kind of blitzed through this. Current node is bigger. The top middle 5 is visible from the top and the right, that makes. Oh, I see. Still? Really? kind of just totally inverted the logic here. We'll do this again. This is so bad. So if something is obstructing the view, that means it's higher or equal to the current. This right? Okay, we are definitely not leaderboarding here. So C equals ND. 20. We're missing a tree. Between it and an edge. So everything here is visible. This is visible, so is this. It's visible from that edge. This you can't see. For 1 you can definitely see. 0, 2 you can see. You shouldn't be able to see this because it's being blocked on all sides, yeah. 2, 2 is also being blocked, you can't see it. 4, 2 you can see it from this edge. Oh, 4, 2, 3, 2, yeah. And then 0, 3, of course you can see. You can't see this one, it's blocked. You can see this from this edge. You can't see this. And you can see that, and then 1. Huh? 0, 1, 2, 3, 4. And then 0, 1, 0, 2, 0, 3, 0, 4. Why Why am I missing a tree? I'm very confused. Which one in the interior is visible? You can see that 5. You can see the top middle 5. Top right 5. Yeah, it's missing. This is on the edge. Oh, we should be able to see 1, 2. Right? We'll slow down a bit because I definitely missed the leaderboard, but we basically just have to kind of flare out from each side and make sure that the next thing is visible. We're making this a lot harder than it has to be, I think. So we should be able to see 0, 2, right? So it's this one that's being problematic. So when we're moving in this direction, we're going this way, we should see 0, 3, 0, 4, oh. Okay, it's that. Right? Okay. Yikes. Oh, we are very slow today. We do not want to print you anymore. Okay, let's say 2. To measure... The elves don't care about distance, she's taking the memories. Okay. Stop if you reach. You can see 1 tree. Okay, I see. Distance. So I guess we always start with 1. P and stores, and we print things out. So the middle 5 would be 2, 1. We get 1 tree going to the right, 2 trees. Stop if you reach an edge or at the first tree that is the same height or taller. Oh. Let's see one tree. Looking left, its view is blocked immediately. You can only see one tree. Let's see two trees. Looking down, its view is blocked. Actually, you see. Oh, okay. So this one. We want to stop if we let me just make sure I understand this correctly. Okay, so I think it's like we want to stop if the current thing is, yeah, oh no, that should be the right logic though. What is going on here? So we can see, oh wait, oh shoot. Oh, that's okay. We can always just see one tree, I think. No. I guess we have to increment one here. Oops. Why am I not? Yeah, okay. Sure. Oof. Okay, kinda rough day. It's time to travel forward in time, and we'll go through the question. Okay, we should be back after time traveling now, in the present. So yeah, today didn't go so well. In theory, this should have been the type of a day that I actually do okay in, but I think I skimmed too quickly, and I didn't think about the best way to do the problem, unfortunately. So let's just hop into an explanation. So the problem input is a bunch of numbers, and this represents I guess a bunch of trees in the woods, and the number, I guess like how big the number is, represents how tall the tree is. And a tree is visible from the edge. So for example, this tree you can see from the edge because there's only a shorter tree in front of it from the north. And so if you were standing up here on the north, you could see that tree. Obviously, every tree on the edge is visible by default because nothing is obscuring it from the edge that it's closest to. But you have some trees like, for example, this one right here. It's being boxed in by a bunch of super tall trees, and so you can't see it. And so all this question is how many trees are visible from outside the grid? I think the way I was trying to do it initially was basically the problem, but in reverse. I was trying to see how many trees you could see walking in. And I don't think that probably actually works very well, because really what the logic you want to do and what I ended up implementing after I thought about the problem some more was you pick a point. So for example, this 5, and you just want to explore out in every direction to see if it's visible. So the rule specifically is a tree is visible if all of the other trees between it and an edge of the grid are shorter than it. And so this 5, here, let's find a good example. Obviously this 5 is not visible from this side because the 6 is blocking it, but it is visible from the east because there's only shorter trees in front of it, if you were standing right here where my mouse is. And so the logic you want to do is just, for every point, you can basically try to explore all the way north, see if you can reach the edge, all the way to the left, all the way to the right, and all the way down. And if any of those results in something that can be seen from the edge, that tree is visible. So how do we do that? Well, I'm just gonna go delete all of this, I think, and we can just rewrite it in a cleaner way. Sure. So what are we doing here? Well, we're gonna parse the problem input first, just so that I can explain it easier. Pretend this day object is just iterating over the lines in the file. So we're gonna create a dictionary to make a sparse matrix, I guess, and key it with the x and y values for each of the points. So if I were to say for kv in grid.items, print kv, it looks like this. So we have each of these points by x, y, and what character it is, I guess. It's like, 3 is here, and then the 0 is at 1, 0, this 3 is at 2, 0, etc. So this is the grid that we'll be operating under. And the first step is going to be check what trees are visible. So we can say visibles will be part of a set here. And well, what do we want to do? So for every point in our grid, we want to do exactly what we described, kind of search up, down, left, and right. And the way we can do that is by defining this directions grid. So this one represents walking north, I guess, or south, depending on which way you want to look at it. And you just have this as like the delta for your vector in every direction, up, down, left, and right. So we then want to say for every possible direction in DIRS, we want to do what we did, we described. So we start at the point, and we want to keep going until we reach the edge of the board. So how does that work? We'll say the next point is going to be the current point plus the given direction. And actually we should make a copy. So we'll say this. For every direction, we want to, ooh, how did that get there? We're going to want to copy this out so we don't overwrite the variable. So we're going to say p is equal to point, and then while, I guess, we can say the next point is going to be the current point that we're at plus this little delta that we're going. So in this case, we would continuously be adding 1 to the y position to keep on walking as far as we can. And so while np is in the grid, as in it's still a point that's in the grid and not outside of the grid, we want to keep doing this check. So what is the actual check? Well, we stop if we are obscured by another tree, right? So if the current point, so the next point that we would go look at is bigger or equal to the point in question, the tree that we're kind of looking at. Actually, we'll call this tree in grid. Maybe that makes things clear. Is bigger than the start tree, as in it's obscuring our vision, then we want to break. Otherwise, if we make it all the way out to the edge, that means the tree is definitely visible. So we can say visibles.add the tree, and we don't even have to then check the rest of the directions, because all that matters is that it's visible from a single direction. So we should be able to break here. So if it's bigger, we break. Otherwise, we want to add that delta, I guess, to ourselves again. So, oh wait, actually, maybe we'll do it this way. While p is in grid, we'll do this, and we'll say the current point is our next point. I have to check in my head if this is correct, so let's try this out. What do we get if we run this? We get a key error. That's a new one. Why do we get a key error here? Very strange indeed. Oh, of course. We have to separate these things out. So the next x, so it's going to be the next x and the next y are going to be, or dx and dy are separate in directions. When I was solving it, while trying to solve the problem, I was using a point class that I had defined, and you can add those points together. But here, these are just tuples. And so if you add two tuples, I guess we can demonstrate that. If you have a tuple like this, and another tuple like this, what we want to do is add them together so we sum the 2 points like this and get 4, 6. But if you actually add these together, you just kind of append the two together. And that's not actually what we want here. And so what we want to do is say, the next point, we have to, what's the easiest way to do this? We can just say x, y is the current tree. Oh yeah, okay. And the next x is going to be x plus dx, and the next y is going to be y plus dy. And if nx and y is there. Otherwise, x is the next x and y is the next y. And we should do this while x, y is still in the grid. We should do this. And maybe we will... Maybe we don't even need to do this check. We can do... Okay, so this is happening because we're trying to check something like outside of the grid. There's a couple ways around this. One of them is just changing the way that we do the condition check to make sure nx and y is still in the grid. The other way we could do it is just something like this. It's a little complicated. Okay. We should probably parse the characters into integers, actually. Normally, we could have done the comparison just on the strings because the ASCII values are comparable. But if we want to do something like this, where we default by saying, I think we want the default to be like a really big number if the next thing was outside of the grid. Or no, we want it to be a really small number. We want it to be -1, I think. Let me just verify. Does this give us the expected answer? Oh, it doesn't. Oh dear. Oh no, we do want it to be a really big number, I think. No? Oh no. This is, live coding is always a disaster, I feel. Oh, of course. If we don't break out, I guess, then we can do this. And then this should be -1, right? Yeah, okay, this gives us the right value, but I feel like the way that we're doing this logically is a little convoluted. I think there's a way to simplify this. Basically, so we start at a given xy, and then while xy is in the grid, we want to continuously just like walk forward, I guess. So I guess we can just say, okay, maybe this is clear. So the next position we want to go to, say we're here and we want to check here, if we're at this point and we want to go north again, that means we've escaped. And if we've escaped, we're visible from that edge. And so we can just do this. Are we at the edge yet? And if we are, then we're good. So if the next position we want to check is not in grid, that's actually a good thing. That means we're visible. So here we can add the tree and break out of this loop. otherwise, else, if the next position in the grid, it's not on the edge, right? But it's bigger or equal to the current tree we're at. So for example, we're here and we want to look to the left. We're blocked by this tree. It's just as tall as us. So if you were standing on the left side, you wouldn't be able to see this tree. We break without adding ourselves to being visible. So that, I think, should remove the need for that else on the while loop. Method object, oh, we don't need the get anymore. And we called these visibles. Great. Okay. Yeah, so what we're doing here is, again, going through every tree in the grid and checking all directions, left, right, up, and down, to see if we're visible from the edge. And we do that by incrementally going to the next thing and seeing if it's smaller than the current thing. And if it is, we keep on going. And when we hit the edge, we know we're visible from there. So we're good. So the answer to part 1 is just how many trees were visible. So that's part 1. Part 2 is asking to compute this, what do they call it here? The scenic score of a tree. And the scenic score of a tree is, I guess, the product of all the trees that that tree can see. So for example, this 5 here that's bolded here, if you go up, its view isn't blocked. It can see one tree. If it's looking left, it gets blocked by the 5 that's equal to it, so it can only see one tree this way. If it's going down, it can see one tree, but then it gets blocked here, 2 trees. And if you're looking to the right, it can see these 2 trees. And so you take the product of all of those counts, and that's considered the scenic score of that tree. And so every tree has a scenic score, and you want to multiply them all together and figure out what the highest scenic score is for any tree. So how do we do that? We can say scenic scores is going to be a new dictionary here. And for every tree, we want to compute what its scores are in every direction. And so what do? For every direction, we're going to have to compute its score. So how many trees were visible from that given tree? So how do we do that? We can say its current score is going to be 0 at the start. And when we explore in any given direction, we're going to add 1 to the count. So we're going to break. So something important to note here, what are the different conditions? If we break out of the loop, of the while loop here, we're going to, so at the end of the while loop, we've basically explored until we got blocked. So we're going to say scores.append score, right? And then at the end, we're going to have this list of 4 scores, 1 for every direction, and we're just going to set that key in scenic scores to that value. So how do we do that? We'll say the scenic score is going to be equal to 1, and then for score in scores, we'll say scenic score is product of that and s, and then we're going to say scenic scores of that given tree is going to be equal to the scenic score. And I see the typo here. So every time we see a tree, we want to add 1 to that score in that direction. So we're going to say score is plus or equal to 1. Something else to note is that if we get blocked by a tree, we also do see that tree. So we're going to want to add an extra 1 here before we break. And I think that should be correct. So if we do, okay, before we print things out, I guess, we can say print the tree and also print scores. And let's see what we get. does this output make sense? So for the value 5 here, that should be y equals 1 and x equals 2. We have a score of 1 times 1 times 2 times 2, which is what we expect here. And if we look at this 5 here, this should be 2 comma 3 right here. We have a score of 2 times 2 times 2 times 1, which is exactly what we expect. And on the edges, we see a bunch of zeros, of course, because there's many directions where this tree doesn't see any other trees. And so all that part 2 asks is, once we've computed those scores, what is the highest score possible for any tree? Well, that's just going to be the max of any of the values in our scenic scores dictionary. So we can just say the max of scenic scores dot values and remove that print. So if we run it on the test, input here, 8 is the highest scenic score here. And then I believe, if I recoded this correctly, if we run it on the real input here, the answer was part 1 was 1719, and the answer to part 2 is this. So that was today's problem. And then again, I was just continuing to use my magical thing here to make it easier to like demonstrate the code. But if you wanted to have something that works for real, I would probably just do something like file input, right? And then it would just be for line in file input dot input. And this would all work exactly the same. So now, you know, you have your shell, you execute day 8, and you could even just either pass in the file as your input here. Oh, we are going to want to strip that new line off of the line, because otherwise it gets interpreted as a character, and that is wrong. So we can run it like that. Or the nice thing about the file input module is you can also just pipe something from standard input into. So you could just, if you had another source of data, you could pipe it in like this, python3 day8.py. That'd be the same thing. Or of course, you know, you do the redirection this way, inputs 08.text. All of those work. So a file input module, pretty handy for making a flexible Python script that can take either a file in as the argument, or accepting stuff from standard input. But yeah, that was day 8. I kind of don't even want to look at it, but we finished 2000th or something on part 1. Improved to top 1000 in part 2. But yeah, I wasted too much time thinking through the wrong approach on this problem. Which moves us down to 36th place. So still in the top 50. We definitely should have got points on today though, but that's okay. We'll be back for tomorrow after some rest. So thank you for watching.